Welcome to the lecture. You may recall that in the last lecture we had discussed about different aspects of multiple linear regression model. So now we are going to discuss about different small topics which are useful in application. So we will basically discuss various type of diagnostics in linear regression model. Okay, first of all, we are going to talk about press residuals. Based on that, we will define a diagnostic which is called as press statistics. Okay, first we try to understand what is this actually press. But before that, let me tell you the interpretation. The interpretation of press is prediction error sum of squares. Okay. Now, firstly, let us try to understand the problem with the following figure. Suppose this is my x-axis, this is my y-axis, and we have some data points like this. And here we try to fit a line like this. Okay. Now, as long as all the points are lying close to the line, there is no issue, and the fitted regression line will be a good regression line. Now, suppose there is one point which is lying quite away, say somewhere here. Okay. Now, because of this thing, what will happen that the regression line, if I try to fit using all the data, mean the earlier data and this new data point, the regression line may shift to this place. Right. So one can see that the earlier regression line is now shifted in this direction when a value which is quite away from the existing observation is added in the data. Now, there can be two questions. That first of all, this type of extreme values or this type of unusual values, they may be a part of experiment. So in that case, we have to use some other statistical tools which can take care of such unusual observation. The second aspect is that, well, they are not the part of your experiment, but somehow they are appearing in the data set. So our objective is that how to identify such observations from the given set of data which are unusual, and they may be good or they may be bad. So first we are going to discuss on this aspect. So now the next question is how to develop a tool. The idea of developing a tool to identify such observation is very simple. You can see here that when we have all the observation where there is no unusual observation, we have a line which is given by the green color. Now, when we are trying to add an unusual observation here, then the regression line is shifted, and this blue color line is the new regression line. So now, the idea which we are going to use is the following. That suppose we have got a data in which we have got unusual observation. So now, if I try to delete this unusual observation from our data set, and then we try to fit the regression line, then this is going to be the same regression line which is given here by green color. So, based on this idea, we proceed as follows. First step is drop ith observation, and in the second step fit the regression line with remaining observations, and in the third step, using the fitted model which is obtained after removing the ith observation, we compute the predicted value which we are going to denote as say y hat, and I is written inside the bracket to denote that this is the fitted value of yi based on all the observations except the ith one. So, now if you observe, yi is the observation that we have obtained from the experiment, that we have observed. Now, if I try to find out the difference between yi and yi, this bracket I hat, this is trying to give us a sort of residual which is indicating the two values of y. When this unusual observation was added in the model and when this unusual observation is not included in the model. And this is called as press residual. And this press residuals, they help in checking the quality of fit. So that means whatever model we have obtained on the basis of given set of data, this press residual is going to help us. Now we denote this press residual as say here EI. I is written inside the bracket. So this is now we are going to consider as yi hat. Okay. Now based on that, we define the press statistic, and this is usually denoted by press, which is the sum of squares of this press residuals. So now if you try to observe this quantity, what are we doing? We are going to delete one observation at a time from the given data set. We will try to find out the fitted model using ordinary least square estimation or say maximum likelihood estimation, and then based on that we will try to calculate the press residuals, and this process is going to continue for each observation, and then we are going to find out this press statistics. The role of press statistics is this, that it measures how well a regression model will perform in predicting the new data. So you can see now we are moving towards the aspect of forecasting and prediction. So, this is one statistics that will help us in diagnosing that whether the fitted model is going to work well in case of prediction or not. And in this case, a model with a small value of press is desired. Okay. Now, based on this press statistics, we try to define a goodness of fit for the prediction, and we define here R square for prediction. You may recall that in case of multiple linear regression modeling, we have defined the coefficient of determination R square, and we had used it for judging the goodness of a fit of a model. Now, once we have obtained the model, we would also like to know what will be the performance of my fitted model when it is used for prediction. So, in order to develop a goodness of fit statistics, we try to use the press, and we define here a R square like statistic, and which is used for judging the predictive performance of model, and this is defined as, say, R square. Let me write it, R square prediction, this is equal to 1 minus press divided by SST, where this SST is nothing but the total sum of squares which was obtained from the analysis of variance table. And this value of R square prediction also lies between 0 and 1. And this also has got a similar interpretation like as R square. For example, when R square is 1, that means the model is really good for the prediction. This is an extreme case. And similarly, if R square is 0, that means model is not at all good for the purpose of prediction. Now, if we say that R square prediction is equal to 0.92, right, then this value indicates that the model is expected to explain about 92% of the variability when it is used to predict a new observation. Okay, or in simple words, one can say that the model is nearly 92% good for the purpose of prediction. Next, we are going to talk about outliers. What is an outlier? Outlier is simply an extreme observation. Well, now once again we will have here two options. The extreme observation is a part of our study, and this is coming in a natural way from the experimental setup. Or the second thing can be, this is an unusual observation which is not desired, and this is going to affect our model, which is not acceptable. So, in case this extreme observation is arising as a part of the experiment, then we have to think of some other statistical ways to to find out the fitted regression model. And in case this is some unusual observation, so we would like to have some diagnostic statistics and diagnostic test which can tell us on the basis of given set of data that which of the observations are extreme observation and they are essentially an outlier. So, we are going to now work on this line of action. Now, depending on the location, these outliers may have moderate to severe effects on the fitted regression model. So, next question is how to identify them. What should we do so that we can develop a diagnostic for identifying such outliers? In such cases, the residuals help us a lot. So, we are going to consider here the residuals as well as their scaled version, and then we will see that the residuals and their scaled versions are useful in detecting the outliers. Right. So, first we try to understand how this can be done. We had seen earlier that in case if we have some data on say x and y, we try to plot it here on a xy axis, and can we try to fit here a line like this one. Now, suppose there is some observation which is here somewhere here. So, now we try to find out the difference between the observed value of y and fitted value of y. So, one can observe here that in these points the residuals are going to be quite small, whereas in this observation the residuals are going to be quite large. So, now looking at these two residuals, one can say that in case if an observation is going to be outlier here, then possibly the corresponding residual is going to be larger. So, one can say here that the residuals that are considerably larger in absolute values than the other residuals, say 3 or 4 times of the standard deviation from the mean indicate the presence of potential outliers in the y space. So, what are we trying to say here? That in case if a particular residual is considerably larger, then the question comes how large. So, we are saying as a rule of thumb, and the question should be 3 or 4 times standard deviation from the mean. In case if this happens so, then possibly that would indicate that the corresponding observation is possibly an outlier. Now, when we are talking about the residuals, we had seen that we try to define the residual as say epsilon hat, which was yi minus yi hat. Okay. And sometimes it is useful to work with the scaled residuals. So, now we try to talk about some scaled residuals. So, we are going to talk here talk about two types of scaled residuals. First, we are going to talk about standardized residuals, right. The standardized residuals, they are defined as, say here, di is equal to epsilon I hat divided by ms res, and this is same as epsilon I hat divided by ss res divided by n minus k in the case of multiple linear regression model y equal to x beta plus epsilon with k explanatory variables. And you may recall that the value of ms res, that is mean square due to residual, or say ss res, that is sum of square due to residual, that can be obtained from the analysis of variance table. Right. These DIs have they have got 0 mean, and they have approximately unit variance. Okay. Now, these standardized residuals helps us in diagnosing a potential outlier. So, we say that a large value of di, say di greater than 3, potentially indicates an outlier. The next scaled residual that we are going to talk about is studentized residuals, and this is defined as see here Ri, which is epsilon I hat divided by 1 minus Hii times ms res, where this Hii is the ith diagonal element of hat matrix H, which is x transpose x whole inverse x transpose. Okay. And the variance of Ri is equal to here 1. And this also has got the similar interpretation like as di, that a large value of Ri indicates a potential outlier. Right. These standardized residual, or say studentized residual, they can be very easily calculated when we are trying to use a statistical software. Okay. Next topic we are going to discuss is about leverage and influential points. So, obviously, the first question comes, what is a leverage point and what is an influential point? So, let us try to make here two graphics, and we will try to explain this concept through this graphic. These are your x-axis, y-axis, and we have got here a data set something like this, and here also like this. Right. Okay. Now, we are going to consider here two different points. One point is lying somewhere here, let us denote it as say point A, and there is another point here which is lying somewhere here. Let us try to denote it by here point B. So, now if you try to observe, suppose this is our figure number 1 and this is figure number 2. So, now one can observe that in figure number 1, there is a point A which is lying quite far away from the remaining points. the most of the sample observations, they are scattered somewhere here, and this point is lying quite far away. But once we try to fit here a line, the line is going to be like this in case if I try to use all the observation except the observation at A, right. So, when I try to include this A point in my line, the regression line is not going to be changed. Okay. So, in this situation, this point A is lying quite away from the observation, but the regression line is not affected. So, this point is called as leverage point. Okay. Now, we consider the figure number 2. Now, here you can see that in case if I try to use the observation except the observation at point number B, then the regression line is going to be obtained something like this. And again, this point B is lying quite away from the existing point. But there is a difference. The difference is this, that in case if I try to include this point B in the given sample of data, then the new line will be somewhere here. So, what we observe that this point B is trying to attract the fitted regression line towards itself. So, this is called as an influential point. So, one can see that if a point is a leverage point, then the fitted regression line is not going to be changed, and possibly based on that other model properties are not much changed. Whereas, in case if we have got an influential point, then the regression line is going to be changed, and that is attracted towards the influential point or towards the direction in which the influential point is lying. Now, the question is this, these points can be usual point as a part of your experiment, or they can be some unusual point. And in case of unusual point, we would not like to have them in our regression analysis. But the question is that how to identify them, whether the point is a good point or a point is a quote unquote bad point. So, we are going to discuss several diagnostic here. Possibly they will help us in diagnosing whether a point is a leverage point or it is an influential point, and finally whether we want to retain it in our regression analysis or not. So, first of all, we try to talk about the leverage point. And let us try to denote, say as earlier, HII be the ith diagonal observation of the matrix H x transpose x whole inverse x transpose. Right. Now, the rule is very simple. If HII is greater than 2k upon n, recall that k is the number of independent variables and n is the number of observations. So, in case if HII is greater than 2k by n, this implies that point is remote enough from rest of the point. To be considered as leverage point. So, now what we have to do? We have to compute this HII for all the observations, and then we have to simply compare it by 2k upon n, and in case if this inequality is or not. Based on that, I can decide whether a particular point is a leverage point or not. What we have to be little bit cautious that this limit, this 2k upon n, right, this is only a sort of guideline, because it depends on the number of independent variable as well as on the number of observations. Right. Okay. Now we come on the aspect of influential observation. Right. In this case, we are going to talk about two statistics. First statistics we call as df beta s, and this statistics indicates how much the regression coefficients changes if ith observation were deleted, and this is defined as df beta s ji equal to beta hat j minus beta hat j I inside the bracket divided by sigma square I hat I inside the bracket C G J. Now, if first we try to understand what is the meaning of all these symbols. You see, here beta hat j, it is the estimate of jth regression coefficient using all the observations, and beta hat j I is obtained like this, that eliminate ith set of observations and obtained the estimate of beta j with remaining observations. Okay. And similarly, sigma square I hat, this is the value of sigma square hat which is computed after deleting the ith observation. Okay. And the rule now here is very, very simple, that if absolute value of beta sji is greater than 2 by square root of n, then the ith observation warrants examination. Okay. Similarly, there is another statistics which is called as defits. Okay. And defits for the ith observation is defined as yi hat minus yi hat inside bracket and sigma square I hat inside bracket and HII. Right. So, in this case, as usual, HII is the ith diagonal element of hat matrix and yi hat is the ith fitted value with all the observations, and yi bracket hat, this is the value of yi obtained after removing the ith observation. Okay, and in this case means again the rule is very simple, that if df fits I is greater than twice of square root of k upon n, then ith observation warrants attention. Right. One thing in this df beta s and df defits, we have to keep in mind that the guidelines which we have given here, as in this case it is twice of square root of k by n, and earlier twice of square root of n. These are only the guidelines, right? And in practice you may have to look into your data and then you have to take a corrective decision. So we stop here, and in the next turn we will try to consider some more diagnostic and some graphical detection procedure. Till then, goodbye.